In this video, we're going to take a look at a couple other ways in which you can look at the concentrations of solutions, molality and mole fractions. So molality and mole fractions are nice because their concentrations are fixed. There's two other ways in which you can now look at concentrations, but unlike molarity, where molarity is moles per volume, but volume isn't really fixed because as temperature changes, density of substances change, so therefore there's no real set molarity. As you heat up a solution, well then that solution is going to become a greater volume, or therefore cooling it down it gets a lesser volume, so that concentration will have some slight fluctuations to it as the volume changes, the density changes, therefore creating a slight variation in that molarity. But molality and mole fractions are particle based or mass based, so therefore those are fixed. Molality is the number of moles of particles, so how many particles that are dissolved in every 1 kilogram of solvent. So even if you heat up or cool down the solvent in that solution and therefore the volume changes, the molality stays fixed. Same thing with our mole fraction. A mole fraction now gives us a relation between the particles of the solute and the solvent in relationship to each other, and again, changing the temperature, changing the volume and density isn't going to have any effect on the mole fraction concentration either. So again, mathematically, the molality is the number of moles of solute that are dissolved into the amount of kilograms of solvent. Again, slightly different than that of molarity, where molarity is looking at moles per liter, but again, the molality is going to be fixed because the amount of kilograms isn't going to change as temperature changes, creating differences in that density. But however, with water, it is going to be very similar because water's density is 1, so 1 liter of water is roughly 1 kilogram of water. So actually you're going to have a molality and a molarity that are going to be very similar when you're looking at solutions that are made with water. You're looking at aqueous solutions. So let's take a look at what one of these problems would look like. So if I want to determine the molality of a solution that is made from 90 grams of glucose and it's dissolved into 1.5 liters of water, how can I figure out that molarity? So we're going to list out what we know and what we don't know. And I don't know the molality concentration, but I do know I have these 90 grams of glucose. I also know I have 1.5 liters of water. In order to get molality, I need moles of solute and kilograms of solvent. So neither of my two measurements that I already have of my two different substances are in the correct units. So we have to do some conversions here. So our glucose is what's being dissolved in. That's going to be our solute. It's in grams. We need to get it to moles. So we have to convert from grams to moles using molar mass. So we're going to take our 90 grams of glucose and put it over 1. And then using the molar mass, which is 180, we'll put that down in the denominator. So grams of glucose reduces out. That is 1 mole of glucose. So here's my conversion factor, how those two different units relate. And again, my grams reduce out, leave me with moles, and I find there to be 0.5 moles of glucose that are dissolved into the solution. And again, now I need kilograms of solvent, but I have liters of my solvent, my water that's doing the dissolving. So I got to convert that also. So I'm taking my 1.5 liters of water, and I know that every liter has 1,000 milliliters, so I can convert my liters now into milliliters. And I know the density of water is 1 gram of water for every milliliter of water. And then lastly, get from my grams into kilograms. I know there's 1,000 grams in 1 kilogram. And then when I solve this out, I still get 1.5, however it's 1.5 kilograms. And again, the density of water is close to 1. Depending on temperature, it does fluctuate a little, so we'll just use 1 for now. That way it makes it more simpler. There was no temperature given, so we can't give an exact value for that density of water. So we'll just use the 1. And now that I have those proper units for my equation, I have moles of solute, I have kilograms of solvent. I can now substitute those in for my variable. And I find that 0.5 moles of glucose dissolved into 1.5 kilograms of water gives me a molality concentration of 0.33 molal glucose that's in solution. Again, mole fractions, again, is another way to look at the concentration in terms of the number of particles relative to each other. So the mole fraction is the number of moles of either the solvent or solute relative to the number of moles that are in the solution. So we can get it for both the solute and the solvent by pretty much the same equation. Usually we call A the solute and B the solvent, but again it's the number of moles of solute relative to the moles altogether. So the moles of solute plus the moles of solvent, or also then for the moles of solute, looking at XB there, it's the number of moles of our solvent relative to the number of moles of solute plus solvent. So let's take a look at how we solve out one of these problems. So I have a solution that's made from 108 grams of water and 120 grams of isopropyl alcohol. What is the mole fraction for this solution? So I'm going to list out what I know and what I don't know. Well, I know I have 108 grams of water, and I know I have 120 grams of isopropyl alcohol. What is the mole fraction? So what is X sub A and what is X sub B? What is the mole fraction for my solute, and what is the mole fraction for my solvent? So mole fraction, again, is number of moles of solute over moles of solute plus moles of solvent, and also number of moles of solvent over number of moles of solute plus solvent. However, I don't have moles, I have grams, so we have to convert both of those units. So we'll start with the water. I know that 108 grams of water, there's 18 grams for every 1 mole of water, so I put grams down in the denominator to reduce out those grams, leaving me with moles of water, and I find there to be 6 moles of water. I'll do the same for the isopropyl alcohol. 120 grams of isopropyl alcohol over 1. There are 60 grams of isopropyl alcohol for every mole. And I'm going to put those grams down the bottom so they reduce out, leaving me with moles. And I find there to be 2 moles of isopropyl alcohol in that 120 grams. So now I can take those 2 different mole measurements and plug them now into my equations. And my 2 moles of isopropyl alcohol over the 2 moles of isopropyl alcohol plus 6 moles of water, and I find there to be a mole fraction of 0.25 for my solute, my isopropyl alcohol. And then I can do the same with my water, my solvent. The 6 moles of water over 6 moles of water plus 2 moles of isopropyl alcohol, and I find its mole fraction to be 0.75. And then those two add up together to 1, which is a whole, which is good, because my mole fraction should add up to 1, since there's a whole solution. And since there's only 2, actually I didn't have to plug into X sub B. I could have actually just taken 1 and subtracted the 0.25 to solve for the mole fraction for my water. Another interesting thing that happens here is, well, looking at what we started with, those 108 grams of water is actually less than the 120 grams of isopropyl alcohol. But again, by putting in a particle-to-particle relationship, we see there's actually 3 times more water than there is isopropyl alcohol on a particle basis, even though there's almost even, actually a little bit more isopropyl alcohol than there is water by mass.